Welcome, students. Today we'll be learning about the DES encryption algorithm. The DES algorithm was published by the National Bureau of Standards in 1977. It dominated encryption from the mid-70s through the early 2000s. DES was developed at IBM by Horst Feistel and his team. They based it on the Lucifer cipher. The NSA reviewed it before the NBS made it the official encryption standard. DES implements the Feistel cipher structure. It uses symmetric encryption and decryption. The algorithm uses 4 core operations: XOR, permutation, substitution, and circular shift. It's now largely replaced by AES and stronger encryption methods. Now, let's examine the Feistel cipher structure. First, we split plaintext M into 2 L-bit blocks. If needed, we pad the final block to match the 2-liter requirement. It uses only XOR and substitution operations. From the original key K, we generate n fixed length subkeys Ke1 through Kn. The Feistel structure takes a 2-bit input and splits it into 2 parts, L and R. Each L bits long, given a bit input and a subkey. The Feistel cipher applies function F to generate a bit output. Both encryption and decryption use identical operations repeated n times. Let's examine the Feistel encryption process. The plaintext M consists of L and R. In round 2, we perform these steps. Li equals Li1. Li equals Li1. Function output. F takes Li1 and key as inputs. Where I equals 1, 2, n. It runs n rounds. In the final round, Ln plus 1 becomes Rn. And Rn plus 1 equals Ln. The ciphertext C concatenates Ln plus 1 and Rn plus 1. Looking at this diagram, first round of Feistel cipher. Plaintext splits into 2 parts. Left part is L, right part is R. In round 1, let's examine R. R becomes the left input for round 2 unchanged. Now for L. L undergoes an XOR operation. This XOR takes 2 inputs. First input is L. Second is function output. The function takes 2 inputs. First input, subkey key. Second input, R. Function output XOR with original L becomes right input for round 2. In the Feistel structure, the operation iterates n times, generating the final ciphertext. Decryption mirrors the encryption process. During decryption, the ciphertext splits into left and right blocks. In the first decryption round, the left block L in decryption. L undergoes XOR operation. The second XOR input comes from the function output. Function requires 2 inputs. First input is the subkey. This subkey is denoted as Kn, where Dn generates the subkey. The second input is R. Both R and subkey Kn serve as inputs to the function to generate output. This output is then XORed with L. The resulting value becomes the right side input for the next round. Meanwhile, the original R value becomes the left side input for the next round. This describes the Feistel cipher structure and its encryption-decryption process. Let's examine the Feistel cipher decryption. Symmetric to encryption. Using subkeys in reverse. First, rewrite ciphertext C as C 等于 ln 加 Rn. For round D, compute next iteration. Li prime equals Li1 prime. Li 等于 Li1. Function output. Function takes two inputs. First input, Li1. The other input is K. In the final round, L equals Rn. R equals Ln. The resulting ciphertext M is the concatenation of L and R. This completes the FISTO cipher decryption. Now we'll examine the FISTO cipher structure to verify its decryption correctness, to prove that the FISTO decryption algorithm recovers the plaintext, matching the original input. Let's prove this using two equations. First equation, Li 等于 Mi. Second equation, Ri 等于 Li. We'll prove this by induction, starting with the base case. L0 prime equals Ln plus 1. R0 prime equals Rn plus 1. Thus, both equations hold for the base case. Next, the inductive hypothesis. Let's assume I 小于等于 n, where both conclusions hold. L 下划线 I 等于 R 下划线 n1. R 下划线 I1 等于 L 下划线 n1. Now to prove, L 下划线 I 等于 R 下划线 I1. From the decryption algorithm. By inductive hypothesis. From the encryption algorithm. Thus, the first equation holds. R 下划线 I 等于 L 下划线 I1. Performing XOR operation with F function. The F function takes two inputs, Li1 and 9 plus 1. This equals Li1 XORed with Li1 and 9 plus 1. Which results in Li. Then applying XOR with the F function, where F function takes Li and 9 plus 1 as inputs. The XOR operation uses Li and 9 plus 1. Based on XOR properties, XORing identical inputs yields 0. Therefore, the result simplifies to Li, thus verifying the second equation. This concludes our proof of FISTA decryption correctness. Next up, DES encryption steps. The plaintext M is 64 bits long, so L is 32 bits. Key length, 56 bits. Adding parity bits extends it to 64 bits. Generates 16 subkeys of 48 bits each. This means 16 rounds of operations. Looking at DES encryption, here are the steps. Step 1. Set L0 and R0 to IP. IP 等于 initial permutation. M is our plaintext block. The input plaintext block undergoes an initial permutation to generate L0 and R0. 4 iterations I 等于 1 to 16. Perform these operations. Li equals Li1. Li equals Li1. XOR with F function output. Ciphertext C 等于 R16 plus K16. Apply final XOR. DES decryption process. Initialize L0 and R0 with the IP of ciphertext C, where C represents the ciphertext. After receiving the ciphertext, first apply the initial permutation. Once permuted, the result becomes our decryption input, denoted as L and R. Next, iterate I from 1 to 16. Performing these operations. L 等于 R. R 等于 R. XOR with function output. The F function takes RI1' and KI as inputs. The resulting original plain text M consists of R16 and L16'. After applying the inverse IP, once completed, we finally obtain our original plain text M. Now, regarding the DES decryption algorithm, how do we prove its correctness? DES is an implementation of the Feistel cipher system in its practical form. While before the first round, it applies the initial permutation IP. In the final round, we apply IP's inverse permutation. These cancel each other out, leaving the Feistel structure intact. The decryption structure. Through the Feistel cipher proof, we can prove the validity of DES decryption. How reliable is DES? DES security strength. Extensive testing shows DES has strong avalanche properties. The avalanche effect means changing just a single bit in the input M results in significant changes to the output ciphertext C. DES uses 16 rounds, which is adequate. Fewer rounds would make it vulnerable to differential cryptanalysis. However, the key length is too short, at just 56 bits, making it vulnerable to brute force attacks. Structure of boxes. Initially, there were suspicions about DES containing backdoors in its boxes, until IBM's team revealed the design principles of the SPOX function, addressing all security concerns. DES remained in use through the 1990s, when researchers launched the DES challenge to break the cipher with a 56-bit key. The key space is 2 to the power of 56, approximately 7.2 times 10 to the power of 16. With current technology, brute force attacks are feasible. In 1997, an online attack took several months. In 1998, a specialized cracking machine reduced the time to just days. In 1999, the combined attack method can break the encryption in just 22 hours. What solutions do we have? One option is to develop new encryption algorithms. Work on a new encryption standard is already underway. Meanwhile, another approach would be to leverage existing DES infrastructure to strengthen the current DES algorithm. This covers the DES encryption algorithm. That concludes our discussion.